Welcome back, class. So in today's video, we are going to take a walk through some of the other forms of hybridization. So remember, at the end of the last video, we talked about sp3 hybridization, right? And this is where we form 4 hybrid orbitals, and this type of hybridization is invoked or used to explain when we have tetrahedron-based geometries, like tetrahedron or trigonal pyramidal. So now we're going to look at other forms of hybridization that we would need to use to explain other types of geometries. So let's look at something called sp2 hybridization. So as the name implies, right, we are going to be hybridizing or mixing an s and only 2 of the p orbitals. So that means we're going to have what we call an unhybridized p orbital left on our central atom. And so when these 3 orbitals combine, right, again, they mix to give, they're going to give 3 hybrid orbitals, right, because we always get the same number. And those hybrid orbitals are going to form in order to minimize the energy of the bonding environment that we would see where we need to make 3 bonds, right? Remember, that's going to be our trigonal planar bonding environment, where the bonds are going to form approximately 120 degrees apart. And so we get the hybridization, get 3 sp2 hybrid atomic orbitals, where the orbitals are all in the same plane and they are pointing the corners of a triangle, 120 degrees apart. Notice again, the electron density is shifted much toward the bonding side, right, where the bond is going to occur, to help maximize that orbital overlap and minimize the energy there. Make it much more favorable for bonding. Okay, so let's look at how this might play out in bond. So let's look at carbon, right? Carbon is going to be sort of a prototypical example. So we start out with the 2s2p2 here. We hybridize. Our 4 valence electrons will go into our hybrid orbitals, 1, 1. Notice the sp2 orbitals are going to be the same energy as the unhybridized orbital, or at least they're going to be similar enough in energy where the electrons populate 1 in each orbital. So they fill just like we would if these were 4 equal energy orbitals and we were following Hund's rule. We get 1 in each, and then we get 1 electron in our unhybridized p orbital. So we now have this kind of look. We have 1 electron in each of these. And so if we visualize a molecule, this molecule is formaldehyde, something we've looked at before, right? This is H2CO. Remember the Lewis structure? Looks like that. So we have a double bond between the carbon and the oxygen. Now, I will say, sp2 hybridization is often, very commonly associated where the central atom makes a double bond. And we'll see why that is in just a second. So if we look at the bonding scheme, we see our carbon. It has the 3 hybrid orbitals shown here in purple. 2 of those hybrid orbitals take their unpaired electron and they pair it up with a hydrogen 1s orbital, right, with its unpaired electron, and we form the 2 CH bonds. The other hybrid orbital forms a bond with the oxygen, right? So where the oxygen, notice for the oxygen, right, we just simply utilize standard atomic orbitals, right, where we're showing here the p orbitals, right? So we're showing 1 p orbital here and one p orbital here. Now, there's another p orbital, but it's filled already. It's going to be one of these lone pairs. Right? And so we sort of don't think about it, or we don't utilize it here. So now we have this unhybridized p orbital on carbon with one electron. Well, what does it do? Well, remember, we have a double bond here. So to form the other part of a double bond, right, we can't form two bonds in the same place, right? So the second part of our double bond, or the second pair of electrons that we share, can't occur in the same way, right? We can't have the same end-to-end overlap that we have here, right? We have to have a different kind of bond. And so that bond is formed by an unhybridized, in this case, p orbital. It could also be an unhybridized d orbital in other molecules, but more commonly an unhybridized p orbital, and they overlap on the top and the bottom. So if we think about the lobes of that unhybridized p orbital, right? If I would imagine that unhybridized, it would be here and here, and oxygens would be here and here, right? And these two come together with both lobes forming this overlap. So there's sort of two parts to this bond, one top, one bottom. And this forms the second part of our double bond. So we have one part on this end-to-end overlap made with one of carbon's hybrid orbitals, and we have another part that's shown above and below here that is made with the unhybridized p orbital of carbon. And this is how we get a double bond. Now, these bonds have names, right? The end-to-end overlap is called a sigma bond, and the lobe overlap, or two-part overlap above and below, is called a pi bond. And on the next couple slides, we will dive a little more detail into explaining the difference between these sigma and pi bonds. So one last thing before we move this is notice the geometry here, right? Just because, you might wonder why we didn't invoke hybridization on the oxygen. But notice the angles here, right? The sigma bond and the pi bond for the oxygen are 90 degrees, right? So we don't need to hybridize because it can make the sigma bond with one of the unfilled. So remember, oxygen is going to look like this. It's 6 valence electrons. So the 2s and the 2p, so these two orbitals here are going to be the lone pairs. These two unhybridized, right, are these two other half-filled p orbitals. One is going to make the sigma bond here, and 90 degrees from that, right, is going to make the pi bond. Right? So we don't have any need to invoke hybridization on the oxygen to explain the bonding environment. So again, we don't do it just because. We only do it when we need to. And again, most often, that's only necessary on the central atom. So let's look at these two types of bonds in a little bit more detail. So first we have the sigma bond. Sigma bond, for just an ease of explaining it, is an end-to-end overlap. Right? And so this is the bond that we form along the bonding axis. The pi bond is sometimes called a side-to-side overlap, and where a p orbital, or again, sometimes a d orbital, where the two lobes, right, make two sets of overlaps, one in the upper lobe, one in the lower lobe, to give this sort of shape of orbital where we have two areas of overlap from the two areas of the p orbital. And it's that side to side that we think about, and that's a pi bond. Okay, so we have sigma and pi bonds. And as we saw in the last one, a double bond is made up of a sigma and a pi. So put those in words, right? A sigma bond results when we get that along the axis, bonding axis, end-to-end overlap. It can involve standard or hybrid atomic orbitals. Right, some examples, right? We can have an S to an S, a P to a P. We can have a hybrid to a hybrid. Or we can have an S to a hybrid, or what we saw in the other one, and what we just saw, we can have a P to a hybrid, right? We can have some sort of standard orbital interacting with a hybrid. So there's different types of combinations we can get to form a sigma bond. A pi bond, again, is that parallel or side-to-side overlap. And it's always going to be perpendicular to the bonding axis. Right? So if we imagine the bonding axis running between the two atoms, the pi overlap is either going to be, if you want to imagine, above and below, or front and back, just depending on, which plane it occurs in, but it's going to be perpendicular to the bonding axis. And this is going to occur typically between two unhybridized or standard p orbitals. Now, this pi bond is weaker, right? It's not as strong as the end-to-end overlap, and so sigma bonds are stronger than pi bonds. Now, one of the manifestations of this pi bonding helps us explain what we witness or what we observe when molecules have a double bond. So, one of the things that we know about atoms with a single bond, such as something like 1,2-dichloromethane, where we have a single bond here between the two carbons, we see free rotation around that single bond, meaning that the chlorines are not locked into being in one particular location, right? These, in essence, spin, and so on average, that chlorine is located, right, at all the positions of that tetrahedron, if you will, in terms of orientation in space. But when we have a molecule that has a double bond, like 1,2-dichloroethene, right, then we have restricted rotation. So by having that double bond and not just having a sigma bond, but having a pi bond in place, it locks this rotation, right? We can no longer rotate. We can sort of think about the pi bond as a lock. It's like putting cuffs on the bond. So you have this connection above and below that it doesn't allow the rotation anymore. And so therefore, the chlorines are locked in position wherever they come onto the molecule. So what this results in is it gives us different forms of a molecule, which we call isomers. And this is not the place where we get into talking about detailed isomers and different things. We learned a little bit about naming, right? Organic compounds back when we did naming. And so we should probably recognize the ane ending, meaning we have single bond between the carbons, and an ene ending is indicative of a double bond in the molecule. Now, if you're going to take organic chemistry, you learn much more about isomers, but I'll just point out here that we have two isomers where the chlorines are on the same side, if you will. So, let's say they're both pointing toward us. And we have one where they're on opposite sides. And so these are two forms of this molecule here. Now, yes, I can see people probably thinking that you could draw other forms like, where the chlorines are both over here. Now remember, that's going to be a different molecule, right? Because in that case, both of the chlorines are connected to this carbon. And so that's going to be that's not going to be 1,2-dichlorine. It would have a different name because the 1 and the 2 here indicate that one chlorine is on the 1 atom and one chlorine is on the 2 atom. And so that's going to be a different molecule. So in terms of the 1,2-dichloroethene, we can either have the chlorines both on the same side of the molecule or on opposite sides, and these are called cis for the same and trans for the opposite. And these molecules are going to be different molecules, right? They're going to have different physical and chemical properties. They may behave different. They're going to be different molecules. And so having these double bonds leads to the formation of isomers, or different forms of the molecule. So again, there's some real world consequences or real world properties that we see with the presence of, in this case, a double bond, and understanding a little bit about how these bonds form, and the idea of sigma versus pi helps us explain this behavior. So again, we're using the bonding theory to help us understand the properties, right? To explain what we observe. Okay, let's continue our look through different hybridization models. So we have what's called sp hybridization, right? And this is going to be associated with linear or only 2 electron groups. So you can see we're kind of going down in electron groups from 4 to 3 to 2 here. And as we might be catching on here, since we're using an s and only one of the p, we're going to be left with 2 unhybridized p orbitals, and we're going to have these 2 hybrid orbitals, and they are going to form in a way that gives us 2 orbitals facing 180 degrees apart from each other, right? So having those bonds as far apart as possible, again, the bonding environment, we have 2 electron groups. This is also associated with the presence of a triple bond, or in the case of CO2, 2 double bonds. So what that's going to entail, right, is the formation of not 1 pi bond, but the formation of 2 pi bonds. Now, those 2 in a triple bond, those 2 pi bonds can be between the same 2 atoms, or if you have 2 doubles, you have obviously 1 pi bond for each double bond. And so, but we need the 2 hybridized in order to form those 2 pi bonds. So if we think of the overlap here, we have one of the sp hybrid orbitals bonding with the hydrogen in this case, one of them bonding with the carbon to form the sigma part of our triple bond. So this molecule is this molecule here. And then to form the other parts of our triple bond, we have to form 2 pi bonds, right? So a double bond, we had to have 1 pi bond, and a triple bond, we have to have 2 pi bonds. And notice those pi bonds are located at 90 degrees from each other. Now, notice in this case, both carbons here underwent hybridization. So the sigma bond is made from an sp hybrid on both carbons, and the pi bonds are made from an unhybridized p orbital on both carbons. And those 2 unhybridized p orbitals are, of course, going to be 90 degrees apart from each other. And so the pi bonds sort of form like a paddle wheel shape, right? One of them is above and below, the other one is front and back, right? So they're spaced out, if you will. So that's sp, right? Linked with 2 electron groups, linear geometry, when we have triple bonds or two double bonds. Now, the last two types of hybridization I want to talk to are associated with expanded octet structures. So one of the types of deviations or exceptions to the octet rule that we talked about was expanded octet. So 5 electron groups or 6 electron groups. And so we're going to look at those bonding schemes by utilizing some different hybridizations. So we're going to start with sp3d. So remember, that's 5 electron groups. And in order to create the bonding environment or to match the bonding environment, we're going to need 5 orbitals that are equally spaced, or that are spaced in a trigonal bipyramidal environment. And so to make 5 orbitals, we have to start with 5 orbitals. So of course, we only have 4 if we just use s and p, so we need to pull in a d orbital. Again, and using this explanation, right, it's another piece of information of why things like oxygen and nitrogen can't do this, right? They don't have readily available d orbitals in the second level, right? So this is why this is one of the reasons we only see this behavior when we have bigger orbital or bigger atoms in the third period and below, because now those d orbitals are there and available. So we take the s, all 3 p's, and a d, hence the name sp3d hybridization. Again, they get blended, and we form 5 hybrid orbitals oriented in the shape of a trigonal bipyramidal. Of course, we have 4 unhybridized d orbitals that, typically don't actually get involved. There are times when these can get involved if we, for whatever reason, if we have a structure that forms a double bond within a trigonal bipyramidal environment, then we would invoke one of those unhybridized d orbitals to make the pi component. But we can see, so notice the fluorine here doesn't undergo hybridization, right? It just uses a p orbital to make its one bond with each of the sp3d hybrid orbitals of, in this case, as. And this is going to be present, right, in not only trigonal bipyramidal, but also all of the derivatives of that where we have lone pairs. Remember, the only difference, just like we saw with sp3 hybridization, is that when you see these geometries, there's already going to be one of these hybrid orbitals have a paired up group, or paired up set of orbitals, or excuse me, a paired set of electrons, which are going to occupy that lone pair. So this kind of hybridization can also be used to explain or to look at the shape of any of the shapes that have 5 electron groups. And if we keep going to 6 electron groups, of course, we get to sp3d2, where we're going to utilize a second d orbital in our mixing, and the hybrid orbitals that are formed are 6 equal orbitals pointing to the corners of a tetrahedron, or excuse me, to an octahedron. And in just one example, like SF6, again, the fluorines remain unhybridized, and they bond with the hybrid orbitals of the sulfur atom. Now, just like in sp3d2, this scheme can also be used to illustrate or to explain the bonding in square pyramidal and square planar. So sp3d2 is linked with 6 electron groups. Now, of course, you see the 90-degree bond angles, right? So we're seeing the prediction or the matching of the observed bond angles and the electron arrangement of the hybrid orbitals here. Okay, so let's sort of take a quick review here. So we've gone through 5 types of hybridization. right? And we've seen how these are utilized to match or explain the geometry that is predicted via Lewis and Vesper theory. And as we've already mentioned, right, Lewis theory and Vesper theory do a really good job of giving us basic geometry. So invoking valence bond theory is not invalidating Lewis theory, right? And that's one of the things we need to remember. It helps us go further our knowledge about some of the basic predictions of Lewis theory. So we're not throwing out what Lewis theory gives us. We're utilizing it because we know that it makes correct predictions about the basic shapes of molecules, right? We have empirical data that says that this is the geometry of the molecule, and it matches up well with what Lewis theory and Vesper predict. What valence bond theory and hybridization serves to do is help us explain how that bonding scheme can come about utilizing the orbitals, right? And what we see is that we can't explain these bonding theories using what we have learned as the standard quantum mechanical orbitals, right? There has to be some alteration of those orbitals to match up with these predicted geometries, and not just predicted, but observed geometries that come from Vesper theory. And that's where the hybridization comes, where those orbitals change their shape, where the electron density is going to be located in order to maximize the bonding, minimize the energy. Right? Now, with that being said, right, we have a direct link between the hybridization scheme and the geometry. Or maybe, more we would think about it is the number of electron groups. And so anytime we have 4 electron groups, right, that's going to be linked to the central atom undergoing sp3 hybridizations. If we have 3, sp2 hybridizations. Right? We have 2. We have a linear type geometry, right? That's going to be linked to sp. And of course, that linkage is true for any of the geometries that are linked to tetrahedral but have lone pairs. And so that's why sometimes I think it's useful to link it to the electron groups and understand that relationship to the geometry. We have 5 and 6. These are going to be located to the sp3d and the sp3d2. So when we're actually going about doing this experimentally, well, we want to conceptually understand where these hybrid orbitals come from and how they're doing it, but when we want to just assign the hybridization to an atom, right? We want to say, in this molecule, this carbon atom undergoes what kind of hybridization? Really, the key is to look at the geometry and the number of electron groups, right? That's going to tell us. And so, if I were to go about predicting the hybridization and bonding scheme, this is what I would do. I would first need to go through everything we did in chapter 10, right? The Lewis structure, the Vesper, right? Because that's going to give me the geometry, right? We can't just start off with the molecule and then go straight to the hybridization, right? We need to understand something about the electron environment around that central atom. And Vesper does a great job of doing that. I can then select the hybridization scheme that matches that. Now, we can then also do some more detail work. Now, I will probably not ask you to sketch, right, to draw these out, but you could give me a rough shape of things that are going on. But I'm not going to ask you to actually draw them, but I would expect you to understand what the bonding environment is in terms of labeling, say, sigma or pi bonds, or telling me how many sigma bonds are in the molecule, how many pi bonds are in the molecule, etc. So let's just, for example, I'm going to quickly go back here. So if I were having you do, let's say, this molecule here, and I wanted you to tell me how many sigma, how many pi molecules are in this 1,2-dichloroethane. Now, if I'm talking about the entire molecule, of course, we need to count all of them, right? So this molecule has, in terms of sigma, has 1 sigma here, 1 sigma here, 1 sigma here, 1 sigma here, and 1 sigma here. So it has 5 sigma bonds and 1 pi bond, and 1 pi bond from the double bond. So that's what I mean by assigned sigma and pi bonds. So I might give you a drawing like this and ask you to do it, or I may just give you a molecule and say, if you sketch out the Lewis structure, you should be able to do this, because sigma bonds are going to be in every bond, and a double bond or triple bond are going to have sigma and pi bonds. Okay. So that brings us to the end of our discussion of Lewis bond theory, and one of the things that I want to is to sort of summarize where we are, and that is that Lewis theory is the starting point, right? It's a starting point for doing all of this, right? We want to understand the basic ideas. But valence bond theory sort of extends this and improves it in some ways. So numerically, right, valence bond theory allows us to get much better numbers for things like bond strengths, bond lengths, bond angles, right? It allows us to justify or explain the bonding schemes, right? It's not changing the bonding schemes, but it's allowing the theory to explain the observed bonding schemes. We can't do that without invoking something like valence bond theory. Now, it doesn't do a very good job of explaining resonance. So there's nothing in here that really helps us understand the resonance that's going on. And it still doesn't do a very good job of explaining other properties, like, for example, the paramagnetism, dimagnetism issue that we see with O2. So by no means is it perfect, it's better, right? And we're getting into the idea of quantum-based, utilizing the orbitals that are generated via quantum mechanics. So next time, we're going to wrap up this chapter by talking about one more theory, and that's molecular orbital theory.